So today we start a new lecture, and here we are going to add a center point to the 2K design. So you will see that this is going to give us a better response surface and a better fit. So again, this is lecture 45 of our optimization series, and I am Dr. Ranjan Ganguly. Now we have seen that the two-level factorial design, where the two levels were high and low, is useful when you are looking for a primarily linear relationship of response with respect to the design variables. And this is the case in many experimental situations where you are trying to get a very basic model which essentially captures the mean value and the slope of the variation. So this 2K design works well when your problem is more or less linear, and essentially you can get the slope, the mean value, as well as the sensitivity. Now, one of the things which you can do to this problem is to add a center point. And if you add a center point to the 2K design, you start capturing some of the effects of curvature which are often required if you want to fit a quadratic model to this problem. So in that case, our problem becomes 2K plus 1 point. So that's the 2K plus 1 design. Now, whenever you are performing experiments or you have some stochasticity in your problem, which essentially means that if you perform the experiments several times, the answers you get each time are slightly different. And this happens because there is a uncertainty present in the system. So in those cases, you do multiple center runs. And essentially we say that we have n subscript c replicates at the center point. So essentially we will do this particular replication several times. So in that case, you would have 2K plus nc points where experiments are needed. So essentially what is happening here is that at the center run, several experiments are being performed, and at the 2K points only one experiment is being performed. So now let us look at this problem pictorially. If you have a two-dimensional problem that is k equals 2, recall that 2 to the power 2 is 4 points. So you would have these 4 points in the factorial design or the 2K design or the two-level design. We have been using these various terms at different points. So when you add the center point, it is essentially at the point 0, 0. So again, these are expressed in terms of coded variable. So your center point is 0, 0, and your factorial points are 1, 1, 1 minus 1, minus 1 minus 1, minus 1, 1, where you will recall that 1 is the high perturbation and minus 1 is the low perturbation expressed in terms of coded variables x1 and x2. So this is your 2K design with the center point. Now, once you have the center point, you have a better chance of fitting a second degree response surface. And one center run would be sufficient if you are dealing with a deterministic simulation. Now, let us go back to the linear model. So if you recall, the linear model has y is beta 0, a mean value, and then it has all these terms which can be classified as linear terms, and then epsilon, which is the value which denotes that you do not have a perfect fit on the problem. So if we look at this carefully, we see that there are k plus 1 regression coefficients. So beta 1, beta 2 to beta k, there are k values, and the plus 1 is coming from this beta 0. So that means there are k plus 1 regression coefficients which need to be determined. Now you want to determine these regression coefficients as well as possible. So one of the things you know from statistics or basic mathematics is that we should have a greater number of points where the experiment is run compared to the number of regression coefficients. Now this will typically give you a better fit for the problem. So for example, if we have the linear model, the number of regression coefficients is k plus 1, and we should try to ensure that k plus 1 is less than 2k plus 1. That is, you have more data points in your design space than you have regression coefficients in your model. So we'll try to check if this is true. So let's take different values of k ranging from 2 to 10, and we find the number of regression coefficients, that is k plus 1, in all these situations with design variables k is 2 to k is 10. So k plus 1 would of course range from 3, 4 to 10 plus 1 here. Now if we take the number of runs, let us just first consider the 2k situation, which is the pure factorial design. Then these would be the runs. Now of course in each of these cases the runs are more than the regression coefficients, so we can say that k plus 1 is less than 2k for all values of k 2 and greater, and therefore this is a sufficiently good model for fitting a linear response surface. So if you are going to fit a response surface of this form, that is beta 0 plus all the linear terms, then your 2k design is quite sufficient for fitting such a response surface. But we know that in reality most nonlinear objective functions are better approximated by quadratic functions. And this also is only possible in a small neighborhood, because in a large neighborhood the quadratic itself would not hold, you would require more complicated functions. Now we also have seen that most of the methods such as the Newton methods and so on have been developed using some kind of Taylor series approximation. So we would generally conclude that quadratic approximations are better for response surfaces, and they are more global than the local Taylor series approximation, because response surfaces tend to consider a larger span of the design space compared to the Taylor series. So again, recall that this was our quadratic response surface. It actually contains the linear response surface as a subset here, the beta 0 and the sigma beta x terms, but it also has the quadratic terms here and the interaction terms here. So let us expand this thing out to see what really is inside this second order response surface. So of course there is a constant term beta 0, there are k linear terms here which we have already seen in the linear model. There are also k square or curvature terms, so ranging from beta 11 x1 square to beta kk xk square. There are also interaction terms, and there are several of these terms which essentially span all the terms of top of the diagonal matrix here. So you would have beta 1 2 x1 x2 beta 1 3 x1 x3 all the way to beta k minus 1 k xk minus 1 xk. So these are the interaction terms. So if we now look at all these terms, so if you look at the constant, there is one constant k linear terms here, there are k square terms, and as far as the interaction terms, these correspond to the terms in the matrix which are on top of the diagonal. So there are k square minus k by 2 interaction terms. So we add all these terms together to find out how many regression coefficients are there in this second order model. So it would be 1 plus 2k plus k square minus k by 2, and if you expand this out here, so we take the 2 here, we double here, 2 plus 4k plus k square minus k, so we get 2 plus 3k plus k square by 2. Now this is same as k plus 1 k plus 2 by 2 if we want to write it in a simpler form. So if you multiply this out, you get k square plus 2k plus 1k, that is 3k plus 2. So essentially this is the number of regression coefficients in a second degree response surface. So remember that it's k plus 1 into k plus 2 by 2. So these are the number of regression coefficients. Now let us say we are taking a 2K design with a single center run. Now we will look at the various points and we will observe that for k is 2 and k is 3, the number of points where runs can be made is less than the number of regression coefficients. So again, this is the listing here. You have the values of k from 2 to 10. You have the number of regression coefficients in the quadratic model, that's k plus 1, k plus 2 by 2. So let's check it out here. If you have 2 here, you would have 3 into 4, that is 12 by 2, that's 6. If you have 3 here, you would have 4 into 5, that is 20 by 2, that's 10. So these are the number of regression coefficients. Now the number of runs here is 2k plus 1. So here all these runs are given here. So you can see here that typically the number of runs is greater in most of the cases, but in some cases it may be lesser. So I think here this should be 5, and then we have 9, 17 and so on. So we see that in some cases the number of runs is greater than the number of regression coefficient, especially when k is greater than 3, and therefore we can overfit the response surfaces. And this is a very important concept in response surfaces, is that if you have a desire to have a particularly good design, you should have more points in the domain than the number of regression coefficients. So of course this can be violated in some cases. All this curve fitting business is more of an art than a science, and people have formed response surfaces with less points and they have gotten good results, but that is for specific problems and specific situations. So in general we can say that more points is always better if you have the time to get those points. So we also see that the 2K design with the extra center point is a good way to capture the basic curvature in the design space. And in many situations, if you have a paucity of computational or experimental resources, you may want to consider the 2K plus 1 design, because you generally have a baseline point and you perturb this baseline point to high and low values, and therefore there is no harm in running your experiment or simulation at the baseline point itself. And this especially is useful in terms of optimization, where you have this point x0 where you are essentially starting the optimization process or a starting design, and therefore you can take perturbations around this starting design, and then you can get the 2k factorial points around this starting design or at the square of the vertices correspond to the starting design. So basically this will give you a decent enough response surface, but we will realize that we should have more points. And of course in the next video lecture I'm going to discuss the central composite design, also known as CCD, which adds more points to this 2k plus 1 design, which lets you get a better estimate of the curvature for the problem. And we'll also discuss the face centered design, or the FCD, which is also related to the CCD but is simpler in many cases where move limits are involved. So this terminates our lecture on how we add a center point to the 2K model and how this center point helps you in getting a better response surface, especially if you are trying to get a quadratic response surface. So I'll see you in my next video.